In this video, I want to go through some example reactions. So I'll give us a set of reactants and we're going to predict the product and whether it went SN2, SN1, E1, or E2. And then also I want to give you that list of good nucleophiles, things that prefer substitution over elimination. I had promised that in the last video and neglected to give it to you. And I'm also going to do a quick review. In the last video, we had that table. What I'm going to do is just kind of summarize again, but I'm going to do it based on the degree of our alkyl halide. So the first one, if I have a primary alkyl halide, SN2 is going to be our favored product. So mostly SN2. And this, of course, is going to be with an aprotic solvent. Remember that SN2 reactions, because the leaving group leaves at the same time that my nucleophile attacks, we favor sterically unhindered substrates. So primary methyl are going to prefer SN2. We can get some E2 if I have a strong bulky base. I'm going to put it in parentheses. It's not going to be our preferred product. Remember, E2 does prefer tertiary alkyl halides, but it is possible with primary. Again, it's mostly going to be SN2. That's generally what I'm going to be looking for as the answer. But if you happen to have a protic solvent, a primary alkyl halide, and a strong base, it is possible to get E2. So E2 possible if a strong, particularly bulky base. Remember that the solvent for E2, while it prefers aprotic, it can also work with protic solvents, right? E2 can use a variety of different solvents. So E2 is possible. SN2 is really what we're looking for, though. Remember, this does prefer tertiary alkyl halides, but again, is possible. We're not going to see any SN1 or E1. Remember, those go through a carbocation intermediate. Primary carbocation intermediates are unstable, right? Unstable carbocation intermediates. Do be careful for things that are allelic, right? Things that are allelic look like they're primary at first glance, right? But they're not. Right, this carbon right here is bonded to one other carbon. It's just that that carbon happens to have a pi bond. So if this leaving group was to leave via an SN1 or an E1 mechanism, I do end up with this. It's just that that's not primary, right? It's allelic, so it does have resonance stabilization. So just be careful, right? It's neither one of those that exists. It's the hybrid, remember. So that charge is delocalized over the entire molecule. So just watch out for that. That is not primary. It's allelic. So don't get those mixed up, right? Allelic, not primary. So just kind of a common mistake that I've seen. Secondary alkyl halides. These honestly can do everything. If I give you a secondary one, it's kind of worst case scenario, right? We're going to get both, or all things are possibilities. So we start needing to look at our base, our nucleophile, our solvent. So sorry about that, guys. E1 competes with SN1 if a neutral nucleophile, weak base, and a protic solvent. I don't always give us the solvent. If I don't, it's because I don't think we need it, right? If I think you need the solvent to determine the answer, I will. So just be careful with those. Often we're going to get both E1 and SN1. If I have a neutral nucleophile or a weak base, something like an alcohol or water, and then a protic solvent, something like alcohol or water, right? I can favor E1 if there's heat. So E1 is favored when heat is added. So if I give you a secondary alkyl halide water and then I add heat to it, I'm really just looking for the E1 product this time. So they don't always compete, right? We could put generally. Some exceptions, whether they don't, is if heat is added. The way I would indicate that is I would either write heat above the arrow. That'd be one way to indicate it. The other option is I could put a temperature, so something like 80 degrees. So heat, right? 80 degrees is pretty hot. 0 is freezing, 25 is considered room temperature. So 80 degrees Celsius would be heating that up. And then we do have a list. It's a pretty short list. The easiest way is to just learn it. Of good nucleophiles that are going to prefer substitution over elimination. So these aren't necessarily neutral. They're just good nucleophiles in general. So they could also go SN2. But if you're given a protic solvent and then one of these, they are going to prefer substitution. So good nucleophiles, let's actually just put it in a different color here. This was the list I had promised in the last video. So good nucleophiles that prefer substitution over elimination. And these guys, keep in mind, I'm normally going to have a cation with it. So instead of just iodide ions, I would give you like sodium iodide, that sort of thing. So do be careful. Bromine, SH minus. Again, be careful. I'm usually going to have a cation with all of these cyanide ions. And then acetate ions also. Be careful. I'm writing it here in condensed. I don't always write it in condensed formula, so that would be an acetate ion. Right? I'm just going to put it in parentheses so you don't think it's something different. So all of these are going to prefer substitution over elimination. The sulfur, I could actually put a carbon-based group with it instead, something like that. So SCH3, SCH2, CH3, that sort of thing. So if you're given one of these, a secondary alkyl halide, a protic solvent, we're going to prefer SN1. If you're given a secondary alkyl halide and a protic solvent in one of these, we're going to prefer SN2, and we'll get SN2 on our list here. So E1 generally converts with SN1. If I add heat, I'm going to favor the eliminated product. If I have one of these good nucleophiles, I'm going to prefer the substituted product. We're going to have SN2 if a good nucleophile and an aprotic solvent, and then E2 if a strong base, particularly a strong bulky base. So again, our strong bases, hydroxide ions, NH2, OR minus. We could do the nitrogen with 2 R groups, 2 hydrogens, 1 hydrogen, and 1 R group. These would all be considered strong bases. And then something that's bulky, I could do an oxygen. And it doesn't have to be tert-butyl. I could do isopropyl. That's also pretty bulky. So something where I have branches coming off the first carbon that's attached to the oxygen. So those would be considered big, right? They're sterically hindered. Remember, if we have a lot of steric hindrance, it can't fit in and grab onto that partially positive carbon, right? The one that's bonded to the halogen. It has to grab the hydrogen off the side. So those are going to prefer elimination over substitution, right? That's where nucleophilicity was one of our reasons at the beginning of chapter 7, right? Where nucleophilicity and basicity diverge, right? Where they're not the same if I had a lot of steric hindrance. So bulky bases are going to favor elimination over substitution. Last one, tertiary alkyl halides. If it's tertiary, no SN2, right? 2 sterically hindered. Again, remember the mechanism for SN2 are nucleophiles adding at the same time our leaving group is leaving. So that transition state has all of those electrons all around that carbon at the same time. So too much steric hindrance. E1 competes with SN1, and I'm just going to write C above. Right? If I have a neutral nucleophile, if I have a weak base, I have a protic solvent, I'm generally going to get both of them. Everything I wrote above is still true. So if I add heat to it, I am going to favor the eliminated product. And if I have one of these, I am going to prefer the substituted product. So everything we wrote under the E1 competes with SN1 above also applies here. So C above. And then E2, right? If a strong base, particularly a strong bulky base, essentially C above also for our examples. So with tertiary, it's very similar to secondary. The only difference is I'm eliminating SN2 from our options, right? Under secondary, SN2 was an option. Here, no SN2, just 2 sterically hindered. And then do watch out, we still have allylic and benzylic, right? These can essentially go any of them, right? My carbocation, if I have allylic and benzylic alkyl halides, right? My carbocation has resonance. Things that form carbocations, right? We want the carbocation to be stabilized. And that's why they don't go primary, right? Because a primary alkyl halide or a primary carbocation intermediate is unstable. Secondary and tertiary are pretty decent. Allylic and benzylic are even better because they have resonance. So if you can stabilize the carbocation intermediate, then mechanisms that involve a carbocation intermediate are more likely. So SN1, E1 for these also. And then just watch out, just kind of as a reminder, right? Our vinyl and our aryl halides. These guys, no reaction, right? Remember with these, our halogen was bonded to an sp2 hybridized carbon. And we need our halogen to be bonded to an sp3 hybridized carbon. So no reaction for those. The rest of this video is essentially just going to be some examples that we're going to go through. So I'll give us an alkyl halide and a set of reagents, and we're going to determine SN1, SN2, E1, E2, draw the major product, and then we'll do a couple of the mechanisms also. So my first one, and I'm honestly going to give us probably the same alkyl halide for most of them, the same secondary one. So let's have a methyl group coming out next door. And we're given potassium cyanide and then DMF. So kind of the checklist in my head, I like to look at the alkyl halide first. So we're going to look at the alkyl halide, primary, secondary, tertiary, right? If it's primary, we can rule out SN1 and E1, right? We don't like primary carbocation intermediates, they're not stable. If it's tertiary, we can generally rule out SN2, 2 sterically hindered. Of course, I gave you secondary, so we really can't rule out anything, but that's generally the first thing I'm going to look at. Then I'm going to look at my nucleophile / base. Is it a good nucleophile? Is it a strong, bulky base? What is it, right? Is it neutral? Is it both a weak base and a weak nucleophile? And then I'm going to look at my solvent. Is it going to be protic or aprotic? Other things to pay attention to, do we have heat, right? Remember, heat is going to prefer elimination, so E1 usually, E2 if it's a strong base, but it's going to prefer elimination in general. And then that list of good nucleophiles that we had up here, right? This list is going to be important. Is it one of those, right? Something that prefers substitution over elimination. So we do want to keep that list in mind also. Maybe we'll just copy it down here again. So iodide, bromine, cyanide, sulfur with a hydrogen, sulfur with a carbon base group, acetate. I think that was all of them. I just want to double check and make sure we didn't miss. Yep, we're good. So these ones are going to prefer substitution. So kind of our checklist as we go through them. So alkyl halide for this first example is a secondary alkyl halide. So I can't eliminate anything from my list of possibilities. I'm then going to look at my nucleophile. So what I have is potassium cyanide. We want to remember that potassium is going to be our spectator ion, a group 1A cation. It's not acidic or basic, right? It's a neutral cation from 152. So we're essentially going to ignore that. And then that gives me CN minus. CN minus, right? My cyanide ions is a good nucleophile. I'm going to look at my solvent, and then DMF was on our list of aprotic solvents. At the beginning of chapter 7, I referred you to a couple tables in your textbook that had protic and aprotic solvents. So you do need to know those. So what I have, a secondary alkyl halide, I have a good nucleophile, I have an aprotic solvent. So what is my mechanism for this, guys? Hopefully you're thinking SN2. And I'm just going to draw the product. It would be really, really good practice for you guys to do the mechanism. You are going to be responsible for the mechanism for this. On your exam and problem sets, you're going to need to draw them. So please practice this mechanism. So that carbon, the one that has that methyl group, is not being involved in my reaction, right? My cyanide is attacking that partial positive carbon, right? The one that halogen is bonded to at the same time that halogen, my leaving group, leaves. Because of that, it has to happen with a backside attack. So in my product, cyanide, not bromine, my nucleophile is going back instead of coming forward. Remember that SN2 reactions involve inversion of configuration. So my configuration on that chiral center is going to be opposite from what it was before. You do need to draw the transition state for this, so make sure that that cyanide group, right, my dotted line between that and the partial positive carbon is 180 degrees from that dotted line between the bromine and that partial positive carbon. So again, please practice the mechanism for this one. A second example for us. So I'm using a similar alkyl halide. I'm not putting a methyl group on that second, or I guess third carbon, but I do still have a secondary alkyl halide. And then we will add this alcohol. So again, kind of going through our checklist, it's still secondary. On your tests and problem sets, they won't all be secondary, but secondary are often the more difficult ones. So I want to make sure in the video that I go through the more difficult examples, so that way you guys can do this on your own. So secondary, I'm then going to look at my nucleophile. It is neutral. It is a weak base, right? My alcohol, just like water, right? If we look at water, remember water is amphoteric, right? It can gain a proton and form hydronium ions. It can also lose a proton and form hydroxide ions. So it can act like an acid and a base. And alcohol is very similar. If I was to just replace one of those hydrogens with a carbon base group, right? They're still both bent. They still have two lone pairs. So an alcohol is also amphoteric. It can gain a proton, right? It can act like a base and gain a proton. Or it can act like an acid and donate a proton. So it is a weak base, just like water is. So it's neutral, it has lone pairs it can donate, it can also take a proton, so neutral nucleophile, weak base. I didn't give you a solvent on Honestly, ethanol could also work, this is ethanol, could also work as the solvent. If it did, it would be a protic solvent. We don't really need that for this, right? We know it's not a good nucleophile, so it's not going to be SN2. We know it's not a strong base, so we know it's not E2. So that leaves us with SN1 and E1. I don't have heat, so if I go back up to this, I'm not going to prefer elimination. I don't have one of these, so I'm not going to prefer substitution. So I'm actually going to get both E1 and SN1. So kind of writing some of that down. Not SN2, right? Because not a good nucleophile. Also, if you consider the ethanol also a solvent, it would be a protic solvent. Our nucleophile isn't always our solvent. It kind of takes a little bit of experience to be able to tell when. So if you didn't recognize that or know that, you could just say it's not a good nucleophile and be fine and still get the correct answer. Not E2, because not a strong base. So that is going to give me SN1 and E1. So we're going to get both of these. When I draw my products for this, for SN1, we do need to be careful to see if there's any carbocation rearrangements. There aren't actually any for this one, so we don't have to worry about it. For E1, I also would have to watch for carbocation rearrangements, and I want to make sure I form my more stable product, right? I want to follow Zaset's rule and have my more substituted alkene. And let's actually do the mechanism for this one. And actually, I'm gonna change it on you, sorry. I am gonna put that methyl group here because then we will have rearrangements. So we'll do the mechanism. We're gonna have to do a deprotonation because I have a neutral nucleophile when we do the substitution. And then I am gonna have rearrangements. So if you wanted, and I kind of want you to pause the video, try the mechanism on your own. And then when you're ready to check it, hit play again. These mechanisms you are going to need to be able to do on your own, so it would be good practice. Okay, going through the mechanism with you. My very first step in both of these is that my leaving group is going to leave, right? My rate determining step only involves the alkyl halide. And this is the same first step for both SN1 and E1. Remember, they have the same rate determining step. And this is why they compete with each other. So I do have a carbocation intermediate, and I am going to have rearrangements with this one. So right now it's secondary. Next door to it, right, if I could have my positive charge on that carbon, it would be tertiary and it would be more stable. And then just be careful. It's not the positive charge that's actually moving. It's the hydride that's moving. And then when you do the formal charge calculation, you end up with the positive charge on the other carbon. So like right now, I have one hydrogen on this carbon. So when I do my formal charge calculation, it has a positive charge. What I'm going to do is I'm going to move another hydrogen over to that carbon, and that's going to leave the carbon that this hydrogen is currently attached to, this one right here, only having 3 bonds. So it's going to have the positive charge. This carbon here is going to end up with 2 hydrogens, 2 bonds to carbons, so it's not going to have a charge. So be really careful. It's easy to think that the positive charge is moving. It's that the hydrogen, right, and its electrons, right, it's that hydride is moving, and then that makes the positive charge be in a different spot when I do the calculation. So what I'm doing is I'm taking this bond and I'm moving it over to that carbon. And you can only ever do adjacent carbons. I can't leapfrog. So if you're going to do a hydride or an alkyl shift, it has to be on an adjacent carbon, so right next door to it. So when I do that, I end up with a more stable intermediate. My positive charge is now on this carbon. And again, this is still the same for both SN1 and E1. So at this point, this is where either I'm going to take a proton and eliminate, or my nucleophile is going to add to that carbon, right? My non-octet carbon, and we're going to substitute. So I'm going to do the elimination first. I'm going to draw one of these hydrogens. And remember, we're going to take a beta hydrogen. So a hydrogen on a beta carbon. And I actually have 3 beta carbons. This one, and this one. So it's kind of possibilities if I was to just draw the products. I could have the double bond here. I could have the double bond here. Or I could have the double bond here. This one here is going to be my major product. Remember, our major product is going to be our more substituted product. And then these two are both minor products. They're essentially the same thing. So do be careful. Make sure you read the instructions. If it says draw all possible products, then I want all of them. If it says just the major product, then please make sure you draw the major product because I'm testing you on that. If you draw all of these when I only ask for major, please make sure you label which one's major. If you don't, I don't know that you know which one's major. And like I said, I'm testing you on that, so I will take off. So you can draw them all if I ask for only major. Just make sure you indicate which one the major product is. I am looking for that. We need to finish the mechanism to get to that product. So let's do that real quick. So I'm going to draw one of those hydrogens out. And then we were using, it's kind of up here, but we're using this alcohol. Right? It does have 2 lone pairs on it. So we're going to grab just the proton this time. The electrons between the proton and the carbon are going to go down to make my double bond. And then that's going to give me this product. If I wanted to draw one of the minor products, I would be taking a proton off of one of these end carbons, right? So that one, if I took that proton off, that would give me this product here. So just be careful, make sure the proton you take off leads to the product that you're indicating. So this would be my eliminated product. I'm going to redraw that intermediate. So redraw my intermediate because we need to do the substituted product also, right? We're getting SN1 and E1. So redrawing this. This time I'm going to have ethanol act as a nucleophile and bond to that carbon. So I'm going to bond to that non-octet carbon. I still have that hydrogen attached to it, so we need to do one more step and we need to deprotonate it. I'm going to use another alcohol molecule. Remember, alcohol can accept protons, it can lose protons. If you wanted to use water, that's fine. If you wanted to use the bromine that's floating around, right? We do have a bromine floating around, you could. So ethanol, I need to do that last deprotonation step. And then that's going to get me to this product. This isn't chiral. If it was chiral though, remember that because my intermediate is planar, that alcohol can attack from the front or from the back, right? Or from the top or the bottom, depending on how you drew it, with equal likelihood. So I would get a mixture of stereoisomers. I happen to have 2 methyl groups on that carbon, so that is not a chiral center. Again, if it was chiral, do pay attention to stereochemistry because I'm always looking for that also. So if we were to go back up and write our products here, right, my 2 products, if that's all I was asking for, I'm going to have, right, my major product for my elimination, and then I'm also going to have my substituted product. And again, be careful, it did go through a carbocation rearrangement. So if you're not drawing the mechanism, right, if you're only drawing products, be careful because you're not just putting this group where this group was, right? Anytime you go through SN1 or SN2, it is possible to have that rearrangement. So just be really careful for that. Third example for us. I'm going to use the same alkyl halide. And then that's a potassium bonded to an oxygen, not an OK. And then I am going to give us a solvent. Be careful. I usually put nucleophiles, bases on top and solvents on the bottom, but it doesn't have to be. There's no rule that says that has to happen. I very well could do this. So it's a kind of a dangerous trap. It's really easy to just get used to everything being on the bottom when it's a solvent. And then if it's not on the bottom, you assume it's not a solvent. That's not always true. So just be careful for that. I think I'll leave it like this just so you get another example. So going through my checklist, secondary alkyl halide, so not helpful. If I look at my nucleophile, what I have is acetate ions and then a potassium ion. So I don't care about that. What I have is acetate. It is charged, but the thing to watch out for this one is that it does have resonance, right? And remember, if something had resonance, it was more stable than if it didn't. Back, I don't remember if it was chapter 1 or 2 when we were looking at acidity and basicity, right? We said if something had resonance, it was more stable, so it was less reactive, right? This would be a weaker base. So this is a weak base because it's resonance stabilized, right? Bases are going to go out and donate those electrons. Here, the electrons are tied up in resonance. So it's a weak base, not a strong base. At first glance, it's really easy to see the oxygen with a negative charge and see that it looks kind of bulky and think E2, but it's not strong, right? So weak base, we can eliminate E2. The other thing I'm going to notice is that I am given acetic acid, so I do have a proton on that. So this is my solvent, and it's a protic solvent. Remember, protic solvents, I have an OH or an NH bond. I do have an OH bond. So a protic solvent, so not SN2. So we've eliminated E2 because it's a weak base, right? It's tied up, my electrons are tied up in resonance, so weak base. I have a protic solvent, so not SN2. So what that leaves me is SN1 and E1. Then what I'm going to do is I'm going to go back and I'm going to say, okay, do I have heat? If I do, it's going to favor elimination. Is my nucleophile on that list of things that prefer substitution over elimination? If it is, SN1. If neither, then just like my last example, it's going to do both. So going back up to this list here, I do have acetate ions on it. So because I have acetate and acetate prefers substitution over elimination, this one, I'm only going to have SN1. So kind of be careful, my thought process. I eliminated SN2 because it's a protic solvent. I eliminated E2 because it's a weak base, not a strong base. That left me with SN1 and E1. And then I look, okay, do I have heat? If I have heat, it's going to prefer just this one. Is my nucleophile on that list of things that prefer substitution? If it is, which it is, it's going to be this one. If my answer is no to both of those, then it's going to be both, just like in the last question. So my thought process on that one. So this one, I'm only going to have my my substituted product. And please practice the mechanism. I'm not going to do the mechanism for this one. I'm not going to have rearrangements because I don't have that methyl group next door anymore. So I'm just going to do a straight substitution. So I'm going to have that group attached. So I would have my leaving group leave. I would have my nucleophile attack. I don't have to do a deprotonation step because it's not protonated there. So a pretty straightforward mechanism. It is chiral, we should do that. So I would have both, we could draw both stereoisomers. Remember, the other way that we could write that is I could leave it planar and then I could put the plus minus in parentheses. So either write both of those or it's okay to write it that way. another example for us. We'll do something a little different. That's a parenthesis, sorry. Actually, I'm changing up what solvent I was going to give us. Let's use acetone. Okay, so going through our little list again, primary, secondary, tertiary, I have a tertiary alkyl halide. So we know it's not going to be SN2. Right? 2 sterically hindered for my leaving group and my nucleophile to both be there at the same time. I'm then going to look at my nucleophile / base. Again, I have sodium, which I'm not going to care about. And then I wrote this condensed just so you can kind of get used to looking at it that way. But what I have is my oxygen with a negative charge, and then that's bonded to a carbon. And then the way it's written, those carbons are bonded to 3, or that carbon is bonded to 3 CH3 groups. So what I have is a tert-butyl group, right? The way I usually draw it is skeletal structures, right? That's what I have. So what I have is a bulky base. Bulky, strong base. I am given the solvent, but at this point I don't even really need it, right? I have tertiary, I have a strong bulky base. This is going to be E2. Do practice the mechanism. I'm going to give you some stereochemistry here. So I'm going to have this bromine coming out, and then I'm going to have this methyl group going back. So when you do the mechanism, be careful. This one has to proceed, right, with that anti-periplanar or anti-coplanar geometry. So when I take the proton off of this one, if I was to do the mechanism, I need to use that proton, right? Because my bromine's coming forward, I need to take the hydrogen that's going back, right? There's hydrogen going back and one coming forward, but this is the one we need to eliminate, right? In fact, let's just do the mechanism. Again, I would like you to try it on your own, so please, if you feel ready to do it on your own, just hit pause, try it, and then come back. So let's go through it together. My bromine. I am just going to draw the hydrogen in question on here instead of drawing both of them. And then my big old bulky base. Remember with E2, we're taking that proton at the same time those electrons are going down at the same time that bromine's leaving. And again, remember the bromine's taking those electrons with it, so that arrow points to bromine, right? It's not just going off into space, right? If I drew the arrow like this, it just means that those electrons are like just going off into space, and they're not, right? Those electrons are going on to bromine, so we need to point that arrow to bromine. This is concerted, right? This is all happening at one time, so I do want to see the transition state. And then remember, in the transition state, I want to see that it has that anti-geometry. I'm going to kind of draw it planar because it's going to be easier for me. Like wedging and dashing a dotted line is pretty hard. Like, how do you dash a dotted line? So I'm going to actually put those in the plane when I draw it. So this bond to bromine is being broken. I'm forming a pi bond. This bond to hydrogen is being broken. And then I'm forming a bond to that base. So I'm going to put the rest of the stuff on there because we need it, but the parts, really be careful because I'm looking for this when I grade it, is that this dotted line needs to be anti to that dotted line and in the same plane. So if I wanted to leave that bromine coming out, then the dotted line between the carbon and the hydrogen would have to be going back. I switched them to the plane of my iPad because I think it's easier to draw that way. Which means I need to then switch, right, these other things to being wedged and dashed. Honestly, I'm not going to be all that picky if you want to just get them on there, but one of them would be coming forward. One of them would be going back. Let's actually draw that so it's not such a mess. And then on this other carbon, I have a hydrogen in a methyl group. if I'm switching that methyl group, that hydrogen that was going back to be going down, right? When we rotate it, that means that this methyl group is going back and then the hydrogen's coming forward. All that rotation stuff you guys did in chapter 4 and 5. It is a transition state, so I need to have that double dagger sign on there and in brackets. And then I'm also doing my major product, right? Remember, I'm taking a beta hydrogen away, but I do have 3 beta carbons. So I would have options, right? I'd have minor products also. I am just doing my major product here. So I have my tri-substituted alkene as my product. So E2, right? I have tertiary, so not SN2. I have a strong bulky base, E2. I do have an aprotic solvent. We don't really need it, but it is aprotic. E2 honestly can go with a variety of different solvents. As soon as I saw tertiary and then this big old thing, I knew E2. Another example, I promise lots of examples in this video. So let's look at same alkyl halide and then sodium iodide and acetone. So going through my list, secondary, not helpful, but I always look at it first. On that last one, it was tertiary, which was helpful. I have Na+, which I don't care about, and then I-. I- is a good nucleophile. And then acetone we just had, this is an aprotic solvent. It was on that list that I referred you guys to in your textbook from the beginning of the semester, or the beginning of chapter 7. Sometimes I draw acetone out. Acetone is a 3-carbon ketone, so this is acetone. Be careful, diethyl ether, sometimes I draw out and sometimes I write ether also. Sometimes just ether. Even though we know ether is an entire functional group. This is diethyl ether. Both of those are on our list of aprotic solvents, right? They're polar. I have polar bonds. It's not symmetrical, but I don't have OH or NH bonds. So secondary alkyl halide, a good nucleophile, aprotic solvent. What are you guys thinking? Hopefully you thought SN2. If you did, you're correct. And then I'm just going to draw my substituted product. Do you draw the mechanism for this? Iodide is my nucleophile. This is the one that proceeds with backside attack. So I do have an inversion of configuration. You know, let's do the mechanism. I haven't done SN2 mechanism in this video yet, so it'll be good practice. But again, please hit pause, try it on your own if you feel ready, and then come back and watch. So I'm just redrawing. And then I- is my nucleophile. It's going to add at the same time that that leaving group leaves. Again, bromine is taking those electrons with it. I do need to have those guys opposite to each other. So if I want to have my bromine leaving in this direction, I need to have my iodide adding in this direction. You don't have to draw a C. You can continue to do skeletal structures. You don't even have to put that hydrogen on there, but I am because I think it looks weird if not. Just make sure that your dotted line between the carbon and the bromine is 180 degrees from this dotted line. Right? If I wanted to draw them left and right, I could. If I want to draw them at an angle, that's fine. Right? They just have to be opposite. So if I wanted to do bromine coming in this way, I would need to have iodine leaving in that direction. And then just don't forget to get everything else on there. Like that's perfectly fine. That's a horrible double dagger sign, but I just wanted to show, just make sure, again, if you want to do it crooked, right? Just make sure they're 180 degrees from each other. You are getting graded on that geometry when you do it. And then my product is my substituted product with inverted configuration. So we drew that product up here already. So my rate determining step involves, right, both my alkyl halide and my nucleophile in the same step. One more example for us. You guys are probably getting exampled out. Bromine, same old, make it coming out at us again. And what should we do? Okay, so going through our list, it's secondary. I do have a neutral nucleophile, right? It's not charged. That's what I mean by neutral. I don't mean pH 7 because this is a weak base, right? I have an alcohol again. It's also a weak acid. So this is where we start kind of eliminating things, right? It's not E2 because it's not a strong base. It's not SN2 because it's not a good nucleophile. It's a neutral nucleophile. So then that gives me E1 and SN1 left as options. So then I look, do I have heat? I do. Since I do, it's going to prefer SN2, or sorry, E2. E1, dang, sorry guys. It's going to prefer E1. If I didn't have heat, I'm actually going to get both the E1 and the SN1 product. So I'm just going to get the eliminated product for this one. I am going to follow Zaitsev's rule. I don't have any carbocation rearrangements, so that is going to be my product.